Hello all, I am Dr. Bharati Sagi, Assistant Professor, Department of Electronics and Instrumentation Engineering, VIGNANA VJEC Engineering College. So in the last class we have discussed about modeling of first order systems. Today we will continue the topic towards second order systems. And then in the dynamic modeling of first and second order systems, so we already seen what are the problems encountered, why do we need to model, and how controlling can be attained if you have a model in hand. So, and we already discussed about first order system modeling for a simple tank process in the last session, and we will continue the discussion for the second order systems. So, second order dynamical systems are any systems which are governed by second order differential equations as been seen in this particular slide. So, this is a second order differential equation where the higher order differential is 2. And this is the governing equation for the any second order system, and here the influencing parameters are zeta and omega, and these are the two important second order parameters that we need to identify while modeling any second order system. Zeta is the damping ratio and omega is the natural frequency of the system, which will allow us to understand how the system is going to behave over a period of time before it reaches its steady state value. So in the right side we can see in this figure that this is a plot of the response y of t with respect to time, and the system is dynamically changing its correspondence with respect to time and reaching a steady state value after a while. So depending on the zeta value, the response of this particular process can change like this or something like this or something like this. So any of these behaviors is expected from a second order differential system. So if the zeta value, that is the damping ratio of the system, if it is less than if it is equal to 1, then this will be critically damped case, and the response might look like this. And if it is underdamped, if the zeta value is lesser than 1, then it will have oscillations and it will oscillate, and the oscillations will damp and settle down after a while. So before reaching the steady state, it will have to encounter different peak overshoots. And in the case of zeta greater than 1, the system will be sluggish and will take a lot of time to reaching its steady state value. Okay, so depending on the zeta values, this is how the system corresponds, and depending on the omega n value, how many oscillations it will encounter before it reaches the steady state value and all will be depending. And also the gain of the system also will impact what is the final steady state value it is going to reach once the triggering step input or any kind of input triggering is given. So again, in the second order differential equation, we will be trying to find out the second order differential relationship between the input or manipulative variable u of t and the controlled variable y of t. So any case, any dynamical case, something like which involves mass and damping, inertia and walls. So all these devices or all these cases will make the system second order behavior. And moving on, and there are two very prominent subcases in the second order systems, and generally here we are looking at this level system model here, level system case here. One is non-interacting system and another one is interacting system. So non-interacting systems so we can label any second order system as an interacting or a non-interacting if they are cascaded, which means if they are connected in series, that is one output is serving as an input to the next one and so on, then they are said to be connected in series. If any such systems are seen, then we can understand whether they may be behaving as an interacting system or a non-interacting system. If in a non-interacting system, each individual subsystem, we can see here there are two tanks connected in series, and these two tanks are said to be two subsystems, and two subsystems will behave independently of one another. So the system behavior of this is not affected by the system behavior, the second tank behavior. So this is called non-interacting system, or there is no feedback coupling. There is no feedback coupling. There is no feedback coupling in non-interacting systems. So whereas in interacting systems, the two subsystems are coupled to one another and the behavior of one system will continuously affect the other system. So there is a coupling across R1 because these two tanks are laid in the same level, same elevation, there is a coupling impact of over F1, the flow rate passing from tank 1 to tank 2. Because of these systems, this system is particularly called as an interacting two system model, wherein which, because of the coupling behavior between the two tanks, the whole system undergoes instability, or at least oscillatory behavior, and it takes a lot of time to reach to a steady state value. So the system response is slow, oscillatory due to coupling effect, and it requires a decoupler type of controllers to address this problem. So whereas non-interacting systems are much convenient to handle compared to interacting systems. So now in the forthgoing slides, we will be looking at how to build mathematical model of these kind of systems, how this coupling is going to affect the overall modeling, and where do we see that coupling effect in the mathematical representation. So we'll start with a simple two-tank model. We'll start with a non-interacting system model, and we'll build a mathematical representation, or we'll build a governing equation to represent the controlled variables versus the independent manipulative variable. Here we can observe that this is a two-tank model wherein which we can identify there are two controlled variables, H1 and H2. And there is one independent manipulative variable, as we discussed earlier. This is one independent manipulative variable. So our aim is to identify what is the relationship between H1 versus Q input and H2 versus Q input. So this is our objective to attain at the end of this particular modeling. So let us start with the tank 1. For building any mathematical model using first principle models, our idea is to our initial point is to start with the conservation law, that is rate of mass accumulation is equal to inflow minus outflow. So because this is the mass accumulating bodies, we wrote rate of mass accumulation. If it is energy accumulation bodies, then we will convert this equation or extend this equation for energy systems as well. So looking at tank 1, we know that for this tank 1, the control variable is H1, that is rate of mass accumulation within tank 1 we are going to understand from this particular model, and whose inputs are Q input and Q1. So implying this particular conservation law for tank 1, it looks like dV1 of t by dt is equal to Q in minus Q1, where we know V1 is nothing but area of cross section of the liquid in tank A multiplied by H1 of t. We already know these two are rectangular or square tanks, where A1 and A2 are constant. A1 and A2 are constants. So they are not changing with respect to height. They are at any given instant, at any given height, the area of cross section of the liquid will be same. So therefore V1 is equal to A1 times H1 of t . Right. So now this becomes A1 dH1 of t by dt is equal to Q in, which is an independent variable, and Q1 is a dependent variable. We will write down what is Q1. Q1 can be derived from H1 of t by R1, which is already explained in the earlier sessions, and because we are assuming that this is a laminar flow, this is for a assumption is that laminar flow condition, because of which Q1 is equal to H1 by R, and similarly Q2 is equal to H2 by R2, right? So we will imply this one here, H1 by R1. This becomes A1 R1 dH1 of t by dt. I am bringing all the H1 terms to the left. H of t is equal to Q in of t multiplied by R1. So by taking, because this is a linear differential equation, we can apply Laplace transformation. This becomes A1 R1 S H1 of S plus H1 of S is equal to, so H1 of S by Q in of S gives us R1 by A1 R1S plus 1. This is the first equation we got for tank 1. Similarly, for tank 2, again we apply the same equations. That becomes A2 dH2 of t by dt is equal to, its input is Q1 and output is Q0. So Q1 we already know, which is a derived parameter, H1 of t by R1, minus Q0 we already know, this is a derived variable, H2 of t by R2, and this becomes A2 R2 R1 dH2 of t by dt is equal to H1 R2 times H1 of t minus R1 times H2 of t. So now we can move to the next slide and we'll continue this solving this solution. So this becomes, we can observe this one here, A2 R2 R1, I can write this way, bringing all the H1 H2 terms to the left. So we already have this expression derived from the tank 2, and we will simplify this by applying Laplace transformation. So this becomes A2 R2 R1 S H2 of S plus R1 H1 H2 of S is equal to R1 H1 of S. This is R2, right? And then H2 of S by H1 of S is R2 by R1 times A2 R2 S plus 1. So this is the second transfer function model we got for the second tank height with respect to H1. So we want to look for transfer function model of H2 versus independent variable Q input of S, right? So we can combine 1 and 2 equations to get it. Already we have in equation number 1, this is the equation number 1 we got. H1 by S by Q input of S is R1 by A1 R1S plus 1. So this we are going to use here. So this becomes 2 and 1 R2 by R1 A2 R2S plus 1, and this is from the first equation we have R1 by A1 R1S plus 1. So this gives us R2 by A1 R1S plus 1 A2 R2S plus 1. So this is the second order differential equation. We can see there is a s square term, coefficient s square term in the denominator. So it also indicates a second order differential equation. Therefore, the system behavior H2 and system behavior tank 1 and tank 2 behaviors are independently acting, and they are not coupled by one another. And we can see that finding solutions or closed loop control solutions for these kind of systems is convenient. So where we can also label that this is the gain for overall system H2 with respect to Q input, and this is the time constant from the tank 1. This is the time constant we got from the tank 2. So the system response could be like this. Depending on these coefficients, tau 1, tau 2 and R1 can decide how the system behavior can be. Either it should be damped and to settle down, or it should be over damped, or it should be critically damped. Depending on these zeta values and omega n values that we are going to get after we substitute relevant values of A1 and R1, we'll get to know what is the system behavior over a period of time. So this is about non-interacting systems, wherein which both the subsystems within the cascaded tanks behave independently and they are not coupled. Therefore, they may be slow. The response may be slow, but they are not such that oscillatory or not coupled. So it is convenient to regulate such kind of systems. In the next session, we will look into interacting system model. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.